Okay, wonderful. So let's continue from where we left off yesterday. Um, I think we were looking at the type of um, the list. Okay, and we said, so what did we say? We said, okay, so list is of type to type, and then just like functions. So the list term here is actually a type constructor. So you can construct terms of any list type. So this is all sort of automatic in OCaml, right? We don't have an explicit notion of just talking about list. We always say integer list or string list or something with the polymorphic argument instantiated. But here we have a function. So you can essentially use it like a function. So check list of map would just give you something else, right? So I'll come back to the set notation later, this type set later, but you can apply it like a function. So it expects a so list expects a type. So natural number is a type. I believe you can also do bool, right? And that would also be um, a type. And the type happens to be just a list of bools. And this set we'll come back to later. Okay. So you can, of course, define ordinary functions that you would do in OCaml. So here is a function that checks whether a list is empty. Okay, so it's called isEmpty, and if you just look at the body, right, it should be very familiar. So we are matching with the given list, and if the list is nil, then we return true. It's empty, so we return true. If it is cons, there's at least one element, right? We don't care about what those elements are. We just return false. And then observe that the match with the construct always has an end, right? And this is different from OCaml where we don't have this explicit end, right? So this goes through, and there are several differences from OCaml here. As I mentioned before, we are not using let, we are using definitions. Definitions are more idiomatic. We also have an explicit type argument here, right? In OCaml, this is all implicit. You just say, oh, for any list, this works. Because OCaml's type system allows type inference, we don't have to supply the type explicitly. In Cork, the type system itself is very, very expressive, as I mentioned yesterday. And that is why we have to sort of explicitly provide this argument. And the way you sort of read this function is that isEmpty is a function that first takes some type, right? A, and this A appears here, right? And then it takes a list of elements of that type, right? So A is A here. And then for that particular list, it returns whether it's empty or not. Okay, so that's the idea there. Okay, so that's defined. And we are using nil and cons here. And similar to OCaml, we also have the usual empty list and cons constructors, right? The usual constructors that we deal with. So this empty list is simply a syntactic sugar for nil, and this colon is a syntactic sugar for just cons, right? So this is all obvious, right? Except this additional type argument, everything should be fairly standard so far. And so we are defining these functions. So of course we can compute with those functions. We can actually apply those functions to valid arguments and then get the result out. So here is a command called compute. We will rarely actually do any computations in this course, right? We will prove things and we will be satisfied that the thing that we've proved has certain properties. Here is, but you can in fact compute with the functions that you define. So in order to apply that function and actually run it, so we have to explicitly prefix that with this command called compute. And the idea is that it takes an expression, right? It takes some arbitrary expression and then reduces it and then computes the result of that expression. And what we are doing here is we are calling isEmpty with an explicit nat argument for the type and a non-empty list for the second one. And we expect false, right? Because a singleton list is not empty. And similarly, we can compute with, here is an example which sort of applies an empty list. So we expect true here. Right? Any questions or observations so far on this? Okay, fairly standard. Okay, fine. Stop me if you have any questions, right? You don't have to wait for me to stop talking. Just raise a hand or just shout. I think that's much better than pausing and not asking questions. Okay, so one thing that Coq offers is that it offers a limited form of type inference. So writing this type out all the time is going to be a problematic. It doesn't have type inference where the program does not need any type annotation and then it automatically works. That's not going to work, right? As we mentioned, Coq's type system is very advanced, so that's not going to work. But in limited cases, writing down these explicit types is quite tedious. And Coq has this mechanism to implicitly allow the type arguments. So here is an example. So this is known as implicit arguments. And the difference between this definition of SMT and this definition here is that we are using curly braces here for the type argument, and we were using ordinary braces there. And what this curly braces informs Coq is that try to infer the type of this particular argument, right? You don't have to explicitly provide it. You will infer it from the context. How do you actually infer it? You can infer it from this one, right? If you look at the type of this list, it's a list of A's. So this argument should be an A. That's the intuition that it is using. I mean, of course, it works on most of the things that we want to do, but anything more advanced, it will just fail because this is type inference is undesirable for Coq. But what does this allow us to do, right? The definition, we replace this ordinary brackets with curly brackets, which means that you don't have to explicitly provide this NAT argument, which you provided there. So the Coq is automatically inferring the type. So isempty prime of singleton list is false. And the key takeaway is that we don't have an explicit type here. Given a function that is taking implicit arguments, you can convert that to a function that takes explicit arguments by prefixing that with an at symbol, right? When I write at is empty, then actually we can check it, right? So we can check is empty prime, right? And it says, oh, I'm going to take an implicit argument, right? And I'm going to return a bool. But if you check at is empty prime, so it says I'm going to explicitly take a argument. So the way to read this for all A is it's also a function argument. It's going to take an explicit argument and then a list, and then it is going to return bool. And prefixing a function with that makes all of the implicit arguments explicit. So what happens here is we have to now provide the explicit argument, right? So and then you provide it a singleton list that works out, and it returns false. There is nothing more interesting there. Okay, so that's the simple function. You can also write recursive functions. And the thing with recursive functions in OCaml, we used to write letrec for recursive functions, right? Letrec for anything that is recursive. We are going to compute the length of the list here. And in Coq, we use the term fixed point. And yeah, the reason why it's called fixed point is a bit technical, but fixed point is a more appropriate representation of what goes on than letrec in terms of program proofs. But you can forget that and just say that any recursive function has to be called a fixed point, right? So that's the idea there. And we are computing the length. So it takes an implicit type argument A. It takes a list. And if the list is empty, nil, then it is 0. If the list is non-empty, then it is 1 plus the length of the tail of the list, right? So the definition itself is standard. And you can compute with that. Okay, that's fine. So a list with 2 elements, you get 2 as a result. And 2 is a natural number. And yeah, I put it in a module just so that I don't shadow the definition of the standard library length definition. That's list. We also have option types in Cog, just like OCaml. So and the definition of that is given here. So option is inductive. Inductive means a type. Option is defined for any type A, right? And option itself is a type. And there are two constructors. One is none, right? And none just gives you an option A, right? Option types are like a box, and none just says the box is empty. And sum is the case where the box has a value, and the value that is in the option type is A, right? So the A is this is the same A as this one, and what you get as a result is an option type. So this should be fairly straightforward, given that we encode the same thing in OCaml. And then you can write certain functions. So here is a function called head_op, and what this does is that it gets the head element of a list, right? And because the list could be empty, we have to return something that is an option value. If the list is empty, then we return none. If the list is non-empty, then we return some x, which is the head element. Okay. So, and then you can also compute with this function. So head_opt of singleton list, you're going to get sum 1. Head_opt of empty list, you're going to get none. And the type itself is not resolved, right? So because we are using implicit type argument here, right? This argument is implicit, right? And when I actually give a empty list, I don't know what the contents are. It could be an integer, it could be a boolean, it could be anything else, right? And the way Coq sort of represents unknown concrete types is that it prefixes a question mark before it. So it simply says, I don't know what that option is, right? I don't know what that A is. It is some type which hasn't been resolved. But you can also explicitly provide the type just using the at prefix, right? At head_op makes all of the implicit arguments explicit. So we have to provide the type of the option, right? So the type of the value in the option. So we are saying nat here, and we are giving an empty list. Compare this one, the output of the previous one, right? None, which is option A. Now you get a option nat. Okay, so that's some of that. Yeah, now that we've seen lists and options, right? We can start proving theorems, right? So here is a nice theorem which says that when head_opt is applied to a list of length 0, right? It always returns none. I mean, this is immediately true because you can look at the definition of head_opt, right? If it is if the list is nil, then you get a none as a result. And the way you sort of write down the specification, right? So there are two things going on here, right? There is the implementation here, which has the function definition for head_opt. You also need a way to write the specification. And here is the specification. And what it says is that for all types A, right? And for all lists of type A, if the length of the list is 0, here's the implication, then it says that if you apply head_opt function on that list, then it is equal to none. Right? So that is the specification. We have an implementation of head_opt and we have an implementation of length. We are going to appeal to the definition of head_opt and length in order to make this proof go through. Okay, so our proof obligation is here. I mean, it's this big thing, right? So it's the same as what we have written down here. The first thing we do is for both of the for all arguments, we are going to say, instead of for all, let's just say that you pick an arbitrary type A and an arbitrary type list, and we are also going to move the antecedent of the implication here to the assumption set of assumptions. Assuming that length of list is 0, I'm going to show that the consequent holds, right? So I'm introducing three things: the type, the list, and the length of list is 0. Right? All three things go up to the set of assumptions. Now what do we do, right? So so the way we proceed is that we perform case analysis, right? What are all the possible options for list? So the list could be empty or non-empty. So let's do case analysis. And the way you do case analysis in Coq is using this destruct um, tactic, right? And it takes some term and then destructs it, basically performs case analysis. So when you do case analysis, you have two cases for the list, right? The first is the nil case, and second is the non-empty case. We'll come back to that. So for the nil case, right? So the assumption is that head of length of empty list is 0, right? That is not useful. I mean, we know that that is in fact the case. But if you look at what we need to prove, right? We need to show that if you apply head opt on an empty list, then you get none. And for this, we can look at the definition of head opt, right? If an empty list provider is for list, then we know that it is going to be none. And Coq can just go ahead and apply head opt on empty list, right? And prove that this thing goes through. So if you want to see what goes through, you can first do the simplification. You see none equals none, and then trivial makes it go through, right? We proved it that way. But you can also, trivial also does the simplification. So you can ignore simple and trivial makes it go through. If trivially you can simplify the terms, and then you can discharge it with simple proofs like reflexivity and so on. So trivial helps us not write down simplification, but you can write it explicitly. There is no harm in doing that explicitly. Okay. And the second thing that we want to show is that we want to show the second case, right? The second case is that the list is non-empty. And the assumption is that it says length of a list that has at least one element. This could be anything at all, right? If you read this, the length of a list with at least one element is 0. We know that this is false, right? There is one element, so it cannot be 0. It has to be at least 1. So how do we actually inform Coq that there is a false in the assumption? You can essentially use discriminate to make it go through, because let me comment this for a moment and come back to this one. So if you use discriminate, what discriminate does, just like trivial does all of the simplifications it is able to do. So it simplifies it and then makes the proof go through, right? So if you discriminate, it goes through, because you can see that once a natural number becomes 1, it cannot be equal to 0, right? If it is 1 plus, it cannot be equal to 0. So this is not obvious. So if you want to get more information, you can use simplification, right? Here is the same simple tactic as we used before, and here is a new way of applying the simple tactic, right? So typically what we usually do is we just apply simple just without any arguments, and what simple does is it reduces the terms in the goal, right? But when you do simple with a particular term to reduce, so what I'm doing here, let's move to here first. What I'm doing here is apply simple in this term, length list is 0. It only does simplification there, right? So if you simplify this one, you get, let's come back to why this is S. You get S of length of list. You can sort of think about S as +1, right? It is whatever the length of list is +1. So discriminate knows that that cannot be equal to 0. So discriminate makes the proof good. Yeah, so that is that. Any questions on this proof?
Sir, this works because we have assumed that the length of list can only be greater than or equal to 0, right? That
Yeah, that's
it's
right.
natural.
Yeah, that's right. And that is good point. So if you look at this one, right? We can do check length. Yeah, so by default, right, when you use 0 and 1, they're always assumed to be natural numbers in Coq. So that's a good point.
But what if we have assumed integers, say
The proof, yeah, the proof won't go through because It's actually I'll come back
Can
to
we
that.
prove another subgoal that the length?
Yeah,
Okay,
yeah,
okay.
precisely. So that is what you should do. So um, yeah, you're right. So that is what we should do. We'll come back to that because it needs a few other things that I need to introduce, but we'll come back to that. Okay, good question, Sriram. Um, okay, so let's go back here, right? So there were two goals here, and when we are doing this, you can see that we are only working on the first goal. We are first trying to prove the first goal, and then we are moving on to the second goal. But sometimes what happens is you might have like seven goals, all of which has very large terms. So in order to just allow us to focus on one thing at a time, so Coq has this ability to zero in on a sub goal for the moment, right? And this theorem is the same theorem as before. I'm just using this new ability to zero in on a particular sub goal. So up to here, it's the same, right? And then you can write minus, right? Essentially, minus, if you do it, it is a tactical. And what the tactical does is it zeroes in on the first sub goal, right? You only see one of the first sub goals, right? So that you saw two and you see one. You can prove the first one. And what Cox says is this subproof is complete, but there are some unfocused goals, right? So there are some. It will list all of the unfocused goals. Then you can focus in on the second one again. So essentially, you can think of this like a markdown thing, right? So you can add a list. You can have sublists as well. So if the sublist has a bunch of sub goals, then Coq makes sure that all of the cases are taken care of. So I mean, you can use all of these characters. So you can use minus, plus, star, minus, minus, triple minus, and so on. So sometimes what happens is your proof itself has seven cases, and then each one might have one or two cases. So there we tend to write it using lists and sublists and so on, and that's quite helpful actually. So okay, so that's what I wanted to say about functional programming in Coq. I mean, there is a lot more that is happening, but essentially the core functional programming language in Coq is just the same as what we have in OCaml minus any mutability. So there is no mutability. And the type system is more advanced. We have a tactic language called LTAC, and these are all tactics are all in a different language. They sort of allow us to construct the proof, right? And we saw simple proofs about lists and options in this lecture. So in the next lecture, we'll see the basics of logic programming, right? Um, how do you deal with implications and conjunctions and disjunctions, and how do you go about proving conjunctions and disjunctions? So that is what we'll see in this lecture. Any questions, further questions on the previous one? Okay, so let's dive in, right? So there are actually two goals for this lecture. So the first goal is the explicit goal, right? So the goal is that we will often write proofs with all of these logical connectives, and you want certain tactics to deal with these connectives. We will see all of that in this lecture. But the second goal is to also show that even though you might see these connectives as primitives, right? They're actually baked into the language. What we will see is that you can actually build these connectives out of more fundamental building blocks, right? Just like how we did that conjunction and disjunction from simply type lambda calculus, right? So we said, okay, here is how actually even in lambda calculus, you can build and or and all of these semantics, right? So that is precisely how Coq works as well, and we will see that in quite a bit of detail. Just so that we understand, there is no magic, right? There isn't Coq isn't a very big language underneath. It has very few things, and lot of these things are just standard library definitions. And once you actually understand that, you tend to appreciate the notion of proofs more. So let's dive in, right? Yeah, okay. So first thing is the notion of these propositions that we can prove and program terms, right? So if you sort of focus in on this list, right? List is like a type level function, just like we saw earlier. So it takes a type and returns a type. and then you can define natural number list, right, which is just a type. And if you explicitly ask for what the natural number list is, that type has the type, right? So it should be sort of, um, it should sort of ring a bell in your head, right? So I have this thing called a type, and it has the type. I mean, what is this type, right? And what is its type, right? So these are all the questions that we are going to see, right? So for list, it was pretty straightforward, right? So we had a list, and nat list is just another type, which is obtained by applying this type level function list on this natural number. So if you sort of zero in, right? So we are using similar notation for theorems as well. So we have Curry-Howard correspondence. So what this means is that wherever we write a theorem, they correspond to some type, right? So, and that is a thing that you have to keep in mind, right? So whenever we write this theorem down, this is obvious, right? We are just saying 1 plus 1 equals 2. We will call it the theorem. We won't be more precise all the time. But the way you have to sort of see it is that that's just a type, right? And all we are doing here is we are just saying that's a type. And what is this term obvious fact? That's the proof of that theorem, right? If you can define the proof, that is the proof of the theorem. And the value for the theorem is the proof. So again, Curry-Howard correspondence, right? So wherever you have type, you can consider that as a theorem. Wherever you have a value that satisfies the type, you have the proof. And the analogy is that for a particular type, say natural number, you have multiple values, right? You have 0, 1, 2, up to infinity. So similarly, for a theorem, you could have different proofs, right? So 1 plus 1 equals 2 might have lots of different proofs. Let's actually look at that, right? So here is a theorem. The proof itself is very obvious. We can just make it trivially go through, and then you get some object, right? The obvious fact is an object, and that happens to be the proof of some theorem. And what is the theorem? It is the proof of the theorem. It is the proof of is the type of obvious fact, which happens to be 1 plus 1 equals 2. You can see what that type is. So if you check obvious fact is just 1 plus 1 equals 2, right? And yeah, so I mentioned all of this before. So what the way you have to sort of see this, right? We will sort of use this reasoning often. So whenever I see a term whose type is something that looks like a theorem, that is the proof, right? That is the actual proof that you have in hand that you can manipulate. So this is the evidence. Obvious fact is the evidence that 1 plus 1 equals 2. There can be many evidences, such evidences, right? For example, if you want to prove 1 plus 1 equals 2, I just ask you, right? Intuitively, can you show me that 1 plus 1 equals 2? You can tell me that, oh, go and reduce 1 plus 1. I know how addition works. So 1 plus 1 is 2. So 2 equals 2. And then you say, okay, for any x equals x, and hence 2 equals 2 is also holds. Hence the original theorem holds, right? But you can also do it differently. You can subtract 1 from both sides, right? For whatever reason. And you reduce those terms, you get 1. And then you can appeal to the same equality theorem, right? You can say, I know for all x equals x, I have 1 equals 1, then it must hold. Hence the original theorem that we wanted to prove holds. And the observation is that these two proofs are different, but the theorem that we wanted to prove is the same, right? And the theorem that we wanted to prove is 1 plus 1 equals 2. And that's the analogy, right? For a particular type, you can have many different values. For a particular theorem, we have many different proofs. So what is actually the proof of 1 plus 1 equals 2 that we construct with trivial? So we constructed the proof using tactics, right? I said these proofs are actually valid terms that you can have in hand. So what is it? We can go ahead and print it out to see what it is. So if you print it out, Cox says that obvious fact is EQ right? And and that is the proof for 1 plus 1 equals 2. So EQ is a definition that comes from the Cox standard library, right? And EQ sort of says that captures the intuitive definition that equality is reflexive, right? So it knows that for all x, right, x equals x is true, and it also does some simplification, but that's not important. So we are using this fact, right, in order to show that x equals x. Cox sort of has this definition in the standard library that sort of captures the same fact. And the way you should read this is that I know 1 plus 1 equals 2 because equality is reflexive, right? That's the notion of how we construct proofs in Coq. You can actually go ahead and see what EQREFL is. Yeah, there is a bunch of things that is going on, right? You can ignore all of that. You can just see this particular term, right? There is some type A, there is some X whose type is A, and the proof says that X equals X, right? This proof term, you can use it in order to prove that X equals X. And Coq is exactly using that evidence that we know for all X, X equals X for proving 1 plus 1 equals 2. So that's the way we are actually constructing proofs when we use these tactics, right? There are some known facts about the world. They're all values, right, in Coq's standard library. And we are using those values, we are combining those values in order to construct the proof for the theorem that we want to prove. I mean, this is actually a really nice idea. We are not, um, we don't have a set of axioms which sort of appear out of nowhere. Whenever we say we are using these things from the Coq standard library, they're all built out of more fundamental structures, which is what we will see in this lecture. I mean, any questions on this so far?
Hello, sir.
Yep.
What if I want to do, I want to prove that 1 plus 1.0 is equal to 2?
Good question. So the thing is, 1 plus 1.0 is not a well-typed term, firstly, because that is a floating point number and this is a natural number. And hence, this addition, right? If you, I think, I don't think this works. Yeah, addition is only defined, ignore a lot of the things that happen here. Addition is only defined on natural numbers. This plus is defined on natural numbers. So you need a theory of addition that works for floating point numbers as well, right? So that is there, that is possible. Coq has that support, but in order to prove that, you have to use other theories. We won't see that in detail, but I don't think we'll see it in this lecture. But the lecture notes for the logic lecture has some theories about real numbers. Real numbers are quite interesting, and proofs about them can be quite nasty. So you can do it, but not here. Any other questions? Okay, let's keep continuing. So there is this notion of in Coq, right? There is this notion of things that you can prove and program terms. So we have seen this set appear previously. There is also the thing called prop. So if you check what 42 is, Coq says that 42 is a value whose type is a natural number, nat. If you check what nat is, nat says that it's something whose type is a set, right? And if you look at Coq's documentation, set is defined as the type of all program specifications, right? And the way to sort of think about this is any program data that you can build, they all have the type set. So if you build a list, then the list will have type set. the thing of list of say nat will have the type set. So you can check what set is. Everything has a type in Coq, right? So Coq has this way of infinite universe of types, right? And you can start at the bottom. So at the bottom there are sort of these terms, right, which Coq allows, and they have types. 42's type is nat. Nat has a particular type which is set, and set has a particular type as well, which is type. And similarly, this thing goes on forever, right? So it's an infinite universe. So type has a type. This doesn't seem useful, but everything that you have in Coq, right? Any term and type and everything that you have, they all have types. Actually, Coq's distinction, right? So a cool thing about Coq is in many languages, including OCaml, right? There is this distinction between um, program terms and types. They are sort of separate. So in OCaml, you can write recursive functions and so on, and then you have types, right? And types are limited in what you can actually express. In Coq, these types can appear anywhere. So there is very little difference between terms and types. And that is what is allowing us to actually write these things, right? So if you sort of imagine this, one is a nat, right? And 1 plus 1, if you sort of think about it, is also a nat. But if you look at what we are doing here, we are applying equality, right? And this appeared, if you go back to the previous lecture, it appeared on the right hand side of obvious fact theorem, right? We were using that as a type. So you can lift arbitrary terms in Coq and then make it into a type. And there's a beautiful logic that underlies Coq, which we won't have time to go through. So we saw simply type lambda calculus, right? And there is an extension of simply type lambda calculus. Simply type lambda calculus has simple types. It doesn't have polymorphism. So there is an extension called F omega, and that has polymorphism built in. And Coq's type system sort of is along the same path, right? And it is more advanced in that there is no distinction between terms and types. We can mix these things in arbitrary ways, and that is why type inference becomes complicated as well. But the system actually is simpler than the system for simply type lambda calculus or any other language. We don't have the separation between terms and types, which is quite beautiful actually. So let's just look at what is the type of 1 plus 1 equals 2. We said every term has a type, right? So if you look at 1 plus 1 equals 2, it says that it's a prop, right? 42 was a nat, but 1 plus 1 equals 2 is a prop. The way you should think of prop is that prop is anything that you can prove using Coq, right? It's a proposition that can be proved, but not necessarily hold, right? So not all propositions need to hold. They're all things that for which you can write proofs for. For example, we know 1 plus 1 equals 2 holds. Here I'm writing 1 plus 1 equals 3. That is also a proposition. This proposition cannot be proved because it does not hold, but it is still a proposition, right? And what is a proposition? Proposition is a type. So set is a type, proposition is a type, and types have types and so on. So essentially the takeaway is that there are two worlds, right? So there is a world of program terms, which sort of are classified into set. They cannot be proved, right? They are stuff that are correspond to program data. And then there is the proposition world in Coq. They're all things that you can actually go ahead and prove. Okay. So that's the takeaway from that part of the lecture. Any questions on the distinction between prop and set?
Are
Yeah.
true and false also considered props in Coq, Casey?
Yeah. So good question. So if you do true, they are prop. I think it's small true. That's a bool, right? So lowercase true is a bool, right? That's a value. That's a program term. But uppercase true is a prop, and true can appear in propositions. Does that answer your question?
It does. I think my next question was, it could be an exercise for me later, but how do you go about proving that particular property, the true
Which
property?
one? True trivially holds. So because it's true, right? So you can try it out. We'll come back to some proofs later in the lecture, but it trivially holds.
Mhm.
Okay, so let's continue. So consider this one, right? So we saw that 1 plus 1 is a NAT and 3 is a NAT, but 1 plus 1 equals 3 is a prop. So we are taking two NATs and we are somehow constructing a prop. So how does this work? It's because we are using equality here, right? We are writing 1 plus 1 equals 3, and equals must be something that takes two NATs or more general type and then returns your proposition. So in Gawk, right, Gawk has this wonderful introspection ability. So you can sort of look at the definition of anything and everything. And it is sort of quite nice. I mean, it might give you more information than you can actually process. But the thing that you can do is none of the things are, very few things are actually baked in. Most things are just functions, right? And definitions and so on. So you can actually look at a particular thing and then find out how it is constructed. So equal to is some syntactic notation, okay, that comes from a particular library. First, we have to locate equal to. So this locate is a command that sort of locates notations. So we can locate equal to, and equal to says, oh, that's just a notation. And really, that is the same as equality, EQXY. So whenever you see x equals y, that is the same as EQXY, right? There are two default interpretations. Actually, the second one is what we use. We'll come back to what this one is in a later lecture. So, okay, so we know that the syntax equal to corresponds to EQXY. So what is EQ? So EQ is equality. So this is what we expected, right? We had this inkling that when you write equals, you are taking two arbitrary types and you are constructing a proposition, and that is precisely what happens here. So I take some type A, right, for all A. It takes one value of type A, another value of type A, and then it returns your proposition, right? So that's precisely what is happening when we write this here. So the type itself is implicit, but it's taking one value of NAT, another value of NAT, and then it is giving you a proposition out. I believe you cannot do something like this because it would be a L-type term, right? So this term is L-typed because equality expects the same type on both the LHS and RHS, right? So the thing is, equality can be used to build a proposition um, which captures the fact that two terms are equal, right? And this notion of equality is sort of, I mean, can be proved or cannot be proved. But here is something, right? Here is an intuitive definition of a successor function, right? So given x, it returns x plus one, and here is also a successor, which does given a n, it does n plus two minus one. That is also a successor. And what I'm saying is, I'm building a proposition that these two things are equal, right? So I can build this proposition. It turns out that you cannot prove this proposition. We'll come back to why we can't prove this in later part of the lecture, where we actually see how equality is built. To give you a teaser, equality can only the only proof for equality is that it's reflexive. So it has to be the same term on both sides, and only those terms can be proved. Even though we know the semantics of these two functions are the same, they're not the same terms, and hence the proof won't go through. I'm just writing a theorem to show that you will have this goal, you cannot go anywhere else with this proof, right? So you'll be stuck here. And one additional thing, so we were using QED all the time when we completed proof, right? That's sort of the end for the proof. For proofs that you don't yet have the proofs for, theorems for which you don't have the proofs for so far, you can use this command called admitted. So if you do admitted, So what Cox says is, I don't have a proof for this, but I will take your word for it for now, right? I'll just assume that this is true, right? And I will just go ahead with the rest of the file. And I mean, it highlights it yellow and then puts an yellow here, just so that this thing is very obvious, right? So if there are any admitted in the file, then uh, it comes back to you. So admitted is a very useful thing for building proofs. So what we usually tend to do is to have this high level idea, right? High level idea for how a proof should look like. And we might come up with smaller lemmas that we might need to prove. So usually it's not a good idea to go proving things in a depth first manner. So start with a high level proof, or I need to prove this, let me go ahead and prove this, right? So that's not a useful thing to do, because it oftentimes it is unclear whether the lemma that you have written is sufficiently strong enough to prove the theorem, right? So what we end up doing is we will write the lemma and then we'll call it admitted. And then we'll say, okay, if I assume that that holds, can I go ahead and prove the main theorem, right? And in those places, we actually use admitted. And that's the way we engineer proofs. We will go through some of this in later lectures, how we actually construct proofs interactively. It comes in quite handy, right? And in all of your assignments, what I'll do is I will give you a file which has theorems, and it might have admitted. And all I want you to do is to not use admitted, and the file should compile, right? Which means you have to go ahead and make the proofs. That's what I would expect from the solution to assignments. Okay, so that's equality. So let's just get started with a little bit of propositional logic, and then we'll see how much we can cover. So we all know propositional logic, right? So we've taken multiple logic classes, and we know how these things work. The thing that I'm going to stress here is um, not again basics of propositional logic, but how do you deal with propositional logic in Coq, right? And how are they actually built? Those two things are quite um, go hand in hand, in the sense that you don't need to know how they are built to prove it, but knowing them will actually give you an edge, right? You sort of see, okay, this is this is so simple that um, I can see how I can build my own logical connectives, right? And I can see why these things work. So the usual connectives are all there in Coq. So you have implications, you have conjunctions, which you write as slash and backslash, and disjunction, right? And negation is tilde before the proposition, right? And none of these connectives are actually baked in. So they are not primitives in Coq. By primitive, I mean they are not part of the language, right? They are just part of the standard library. And we'll see how they are actually built. So these things actually give you and, or, and not. So if you check for and, or, and not, you will see that, okay, let's do this all together. So you see that and takes a proposition, another proposition, and gives you a proposition, right? P1, P and Q are propositions, and itself returns a proposition. Similarly, or is proposition. Negation is take a proposition and returns you a negation of that proposition, right? So one thing that you should observe is that there is this arrow here which we use for implication, and we sort of use the same arrow for functions, right? And is a function that takes one proposition, returns another proposition, right? Returns actually a function that takes another proposition and returns a proposition. This mixing of syntax is not accident, right? We are using this arrow syntax for both propositions and functions. And this is very, very explicit. The reason why we use the same syntax is that they are in fact the same. So we'll come back to why that is the case. But the thing is that when you say something is an implication, you can sort of think about them both as a function, right? P implies Q can be thought of as the type of functions that take a P and return Q. or it's a proposition that asserts P implies Q. Both are equivalent ways of looking at things when you see P implies Q. And this again corresponds to this Curry-Howard correspondence that we've been going back to all the time. We'll make it very, very concrete through this lecture. Okay, so let's do some proofs on implications, just so that we get some idea of how to prove things with logical connectors. So this first theorem is very simple, right? All you're saying is P implies P, right? So for all P, where P is any proposition at all, P implies P. So what is the proof of this one? Intuitively, you will say that since you have P, you know P is true, then P holds. You can just, you are given a proof for P, you are just returning the same proof. Or if P does not hold, false implies anything, right? So P implies P holds. So that's the intuitive definition. And Coq proof also follows the same reasoning. So we are going to write the proof. So first we are going to introduce this proposition. Instead of saying for all P, we'll just pick arbitrary P, right? Move it to the assumption. And then we will pick this P, right? We call it P assumed. And the way to read this is P is some proposition, right? P assumed is the evidence that P holds, right? And given that we have evidence P assumed that P holds, we can simply, we have the evidence, right? So P should hold. And that is exactly the way the proof goes through. So we have a new tactic called assumption, right? And assumption just says the goal that you want to prove, right, is exactly one of the assumptions. And hence the proof should go through. We are going to show P. So there is an assumption which is exactly P. And the name of that is P assumed. But because we have that assumption, the proof should go through, right? And assumption just helps us do that. This is the same as what informal reasoning that we've done, right? And let's look at so the cool thing is let's look at how the P implies P proof is constructed. So first, let's look at the type of P implies P. The type of P implies P is actually the theorem that we've written down, right? There is no difference here. So P implies P is evidence for the theorem for all P, where P is a property, P implies P. But what is this actual evidence? So we can print it out. So this evidence happens to be a function, right? And the function takes some proposition. That's the for all, that corresponds to the for all P, right? It takes the evidence for P, right? P assumed is the argument name and P is the type, right? The way to read this is P assumed is the evidence for P. And because we want to prove P implies P, we just return the same evidence. And that's it. That's the actual proof for the theorem for all P, P implies P, right? So, and this is what we are doing, right? So if you sort of think about this, what is the OCaml equivalent of this one? This is just the identity function, right? If you ignore this P argument, I take a P, I return a P. And that is the proof for that function, that particular identity function will have the type alpha to alpha. If you interpret types as theorems, alpha to alpha is the same as P implies P. And hence, the particular value that you have is the evidence. This value that you have here is the evidence that this theorem holds. Okay, so this is Curry-Howard correspondence in practice, right? So we deeply use this idea all through in constructing the proof. So all we are doing, right, when we write these tactics is that we are slowly informing Coq, right, how to build this evidence, right, how to build this evidence. And it turns out that writing this evidence directly is a pain, and hence we use tactics. But you can also directly provide this evidence as an argument, right? So here is a direct proof, right, for P implies P, right? So here is the type. I'm going to directly prove P implies P right? And the way I do it is I just write a function, right, that takes a p, that's the for all argument p, and then I take the evidence for p, which corresponds to this p here, and I return that evidence. And this this term that I construct is the same as the term that I construct using these tactics, right? So tactics are just a nice way to construct these um, complex terms, right? This works for very simple proofs, but as you get more and more complicated, tactics are how we actually build the proofs. And but the key takeaway is that just because you're using tactics does not mean that you're doing something different, right? At the end of the day, you're simply producing a value whose type is the theorem that you want to prove, right? And you can always print the theorems. There'll be complicated terms, but it's always there, right? You have to remember that that is always underneath, powering what is going on. I'll stop here. I think we might be over time. Any questions on this? I recommend going through the part of the lecture, right? Follow it along, and then make sure um, you sort of convince yourself that you understand what's going on, right? And let's leave it there, right? So and then we can come back tomorrow and then finish the rest of the logic lecture. Okay, any questions? Any further questions?
Hello.
Yeah.
So I just want to clarify my understanding of assumption tactic. So it's basically like the subgoal itself is true from the assumption. Is that correct?
Yeah, that's right. So there is an assumption which exactly matches this one. The way to read this, right? I want to show P, right? What is showing P? I want to actually produce an evidence that P holds, right? What is an evidence here? Evidence is just a value, right? Whose type is P? That is the way you should read this. I mean, we will sort of forget this thing as we go along. Assumption simply says, oh, if you want to prove P, there is some assumption whose type is exactly P, and that is what we have, and that is why it goes through.
Okay, got it.
Okay, wonderful. Okay, so let's stop here. I'm sorry I'm taking more time. I'll be on time from next class. So I hope you have a few minutes before the next one. Anyway, bye-bye.
Thank you, sir.
Hello,
Thank
sir.
you. Yeah.
Actually, today there was our meeting, weekly meeting.
Yeah.
So last week I was out of the town, so there